Swayam Prabha. Digital India. Educated India.
So, during my last lecture, I have discussed that how we can incorporate the tilting base and the sloping ground effect in the bearing capacity equation. Now, I have discussed the Henson factors and the factors proposed by the basic. Now, as I mentioned that in my previous class, that these are the 4 cases possible. This is the first case where the eta value, that means the tilting base eta value is also 0, beta is also 0. I mean, beta means the sloping angle. So, that means it is no base tilt, no slope, and then the case 2 where the eta value is not equal to 0 but beta is 0. That means it is not a sloping ground, but the foundation base is tilted. And then the third case where the beta is equal to not equal to 0, but eta is equal to 0. That means that it is not tilted, but it is on the top of a slope. And the fourth case where both can be non-zero component, that means non-zero value, that means it is on the top of the slope as well as the foundation base is tilted one. So, these are the 4 cases is possible. So, I will solve few of the cases, that means one is it is on the sloping ground, another is it is in the if the base is tilted. Okay. You can put both of the effect at the same time, that is the 4th case, but I will solve problems on case 2 and case 3. Case 1 is already been discussed in previous lectures or previous example problems. So, the 4th one is the combination of second and third, so that you can incorporate. So, and then I have discussed these are the factors. So, those are proposed by the Henson and the basic. So, these are called the base ground factor when the foundation is on the slope, and in the base factors if the foundation base is a tilted one, it is a tilted base. That means, the G is the ground factor, B is the base factor. Okay. So, these are the values I have already discussed in my last lecture, that these are the ground factors proposed by the Henson, then the base factors proposed by the Henson, and this is the ground factor and the base factors proposed by the basic. And remember that here this eta and this beta all are in radians in these equations when they are using. For example, the first case where beta by 5.14, this type of case your beta in radian, but when it is in like this tan to the power tan beta, then beta is in degree. Okay, it is mentioned wherever it is in degree, it is given degree, otherwise it is if it is not given anything, that means like this 2 eta tan phi, phi is obviously with tan it is degree, but eta is in radian. So, it is mentioned. So, you put according to that. Now, these are the recommendations proposed by basic and Henson, and remember that here both the base factors and the ground factors are incorporated, but Meyerhoff also suggested methods by which we can determine the bearing capacity of the foundation when it is resting on the sloping ground, but Meyerhoff has not considered the tilting base effect. That means, so that means only you can consider that procedure if the foundation is on the slope, but it is horizontal, not tilted. So, that procedure let me discuss first, then I will go to the example problem. So, Meyerhoff has suggested that if the foundation is on the slope, that means this is the foundation whose angle is same beta and the foundation is on the slope. So, it can be on the surface slope surface or it can be at some depth also. Okay. So, if this is the df and this is the width of the foundation B and this is the distance of the foundation edge from the slope edge and that distance is B, small b. Capital B is the width of the foundation and small b is the distance from the base edge of the foundation or footing from the slope edge. Now, we know that this is for the steep footing, the expression of bearing capacity expression for steep footing is Q u C C N C Q plus half gamma B in gamma Q. Okay, so, this is for the steep footing and for C equal to 0, if C equal to 0, then your Q u will be equal to half gamma B in gamma cube, and for phi equal to 0, that Q u is equal to C n C q. Okay. So, now this is the N C q are the suggested bearing capacity factors. Now, as if you look at this equation where that second term is not present. So, that means here it is assumed that your df is equal to 0. That means this expression is valid if foundation is on the slope itself, not with a depth. Okay. So, that means that this equation that I have written or the proposed by this Mehrov, then where df is taken as 0, because you can see that the second term q n q that term is missing. So, that is only possible if df is equal to 0. So, that means remember that this equation is valid if df is equal to 0, that means the foundation is on the slope. And then this is the height of the slope, say okay, h. Now, another few questions is that how I can calculate this bearing capacity factor. So, this bearing capacity factor it is said this is N C q, okay, N gamma q. So, now these bearing capacity factors is given we can determine from this chart. Okay. These two charts are given. The first chart we can determine the N gamma q and the second chart we can determine the N C q. So, let me first explain the N gamma q part, which can be used if C equal to 0. So, that is the N gamma q part, where this beta is the slope angle. Okay. So, this dotted line is given that if df by b is equal to 0. Okay. And this df by b equal to 1, sorry, if df by b equal to 0, that means foundation is on the slope. So, that can be determined from this form line, and if df by b is equal to 1, so that can be determined by this dotted line. So, what does it mean? That ideally you can see that if df equal to 0, that means this equation is valid for if foundation is on the slope, but this depth effect. Okay. So, this depth effect, foundation depth effect is incorporated in the bearing capacity factors. Okay. If you look at these bearing capacity factors, so now if I have discussed the first part that it is valid if foundation is on the surface, fine. So, if foundation is on the surface, then you use this equation and then you use this bearing capacity factor, that means when dF by B equal to 0, fine. But if your foundation is not on the surface with some depth dF, and then also you can calculate or you can use this expression by using these factors, which those are proposed dF by B equal to U, one case. Okay. So, that means the two cases are given, one is dF by B is equal to 0 when the foundation is on the slope, another is dF by B equal to 1. Okay. Now, if your foundation is in between that, that means that in between 0 to dF by B equal to 1, then you have to linearly interpolate this value. That means, then you calculate the bearing capacity factors for dF by B equal to 0 and dF by B equal to 1, then you linearly interpolate those values between these between your case. That means, that may be less than 1 also. It is in if it is in between 0 to 1, then you interpolate that value by calculating 0 dF by B equal to 0 case and dF by B equal to 1 case, and then you linearly interpolate that value. So, that means, you can use this expression for if foundation is resting with a depth also, but that depth is restricted up to width of the foundation. That means, you can use it up to dF by B equal to 1. So, you can use it for any depth if the depth is within width of the foundation, clear. So, that means 0 to 1, 0 to 1 you can directly get these factors, but it is in between that you linearly interpolate those values and that you put. So, it is clear. So, apparently, if you look at this equation, then you will find that it is only applicable for foundation resting on the slope. Okay, fine, that is applicable for foundation resting on the slope. Then you use that farm lines, but you can incorporate the depth effect also by taking this dotted lines value if your foundation is below the base of the slope. Okay, but that is restricted up to dF by B equal to 1, clear. So, now we can see that beta value is equal to 0 degree, 20 degree, 40 degree. Okay. So, up to 0, 20, 40, because your phi is given up to 40 degree, because if your phi is 40 degree, then you cannot make a slope in normal case more than 40 degree. So, you can see if your phi is equal to 40 degree, then those values are given for beta equal to 0, 20 and 40. Now, if your phi is for farm line also, if phi is equal to 0 degree, then values are given phi equal to 40 degree, values are given for 0, 20 and 40. Okay. But if your phi is equal to 30 degree, then these dotted lines are given for phi equal to 30 degree. And there is a straight line also, which is on this farm line. So, there is also a straight line, dotted lines for phi equal to 30 degree case, which is basically the beta equal to 0. So, if your phi is equal to 30 degree, then beta is given for 0 degree and the 30 degree. And for the farm line also, if phi is equal to 30 degree, then your beta is given for 0 degree and 30 degree. Okay. If the phi is equal to 40 degree, then beta is given for 0, 20, 40. For 30, as we cannot provide beta value more than 30, because then your slope will be unstable. So, we have given values are given for 0 degree and the 30 degree. So, this is for NQ part, where the you can determine the NQ for if C equal to 0, but if your phi is equal to 0, then you can use this NCQ, Okay, NCQ value you will get from this chart. Again, this NCQ we can get for two different cases. One is df by b equal to 1, another is df by b equal to 0. So, your form line is given df by b equal to 0 and the dotted line is given df by b equal to 1. As I have mentioned, if it is within this 0 to 1 value, you can linearly interpolate this value. And for now, if your for this phi equal to 0 case, if your b is, width of the footing is less than h, then you use ns equal to 0. Okay? And now, if b greater than equal to h, then use ns greater than 0. Okay. So, that means it indicates that if your or ns equal to 0. So, what does it mean? Suppose if your b is this width of the foundation, h is the height of the slope. Now, if your b width of the foundation is less than the height of the slope, then you have to use ns equal to 0. That means these dotted lines only. Okay, those are given for n is equal to 0. That means these dotted lines you for n is equal to 0 you have to only use for this case. So, that means your n is equal to 0 you can use for this dotted line is for your df by b equal to 1. So, now if your b is less than h, then you use only n is equal to 0. That means these two cases. So, if this is applicable, if your this is also applicable if your b is less than equal to 0 h and if b is greater than equal to h. So, both the cases it is applicable, but it is applicable for df by b equal to 1. Remember that. So, that means if this n is equal to 0, you can use the both the cases. If your b less than equal to h or b greater than less than h, if b is equal to greater than equal to h. So, but this is applicable for df by b equal to 1. Now, if your n is again it is df by b equal to 0, then this n is equal to 0 you can use for b less than equal to h and b greater than equal to h, both the cases, but this n is equal to 2 and n is equal to 4 you cannot use if b less than equal to h. So, this is only applicable if b greater than equal to h and this is b greater than equal to h. Clear? So, that means this condition you just understand this condition. If b less than equal to h, then use only ns equal to 0. That means, if b is equal to less than equal to h, then you only use ns equal to 0 and case. Two cases, this form line is for the df by b equal to 0 and dotted line is df by b equal to 1. Clear? So, these two cases you can use if b less than equal to h for n is equal to 0. But if your b is greater than equal to h, then you can use n is equal to 0 case as well as n is greater than 0 case. So, that means this n is equal to 0 case you can use for any condition compared to h and b, any condition whether your b is greater than equal to h or b is less than equal to h. Yeah? But if this n is equal to 2 and n is equal to 4 case or n is greater than 0 cases, you can only use if b greater than equal to h, but not if b less than equal to h. Clear? And that, as I mentioned, these dotted lines are for df by b equal to 1 and the form lines are for df by b equal to 0. And these are the angle beta for 15 degree, 30 degree, 45, 60, 90 degree. Okay. Similarly, your this is beta is in degree. This is also for n is equal to 0 case. This is 0, 30, 60, 90, 0, 30, 60, 90, 0, 30, 60, 90. Because now here your phi is equal to 0. So, your ideally you can go for a vertical slope also. So, that is why they have given beta up to 90 degree. Okay. So, 60, 40, but if your phi is not equal to 0, then you have to restrict the slope angle up to the phi value. But here ideally you can go for the 90 degree also, that is why it is given up to 90 degree. So, this is clear. And another thing, that another effect, as I mentioned, the small b, the capital B also we incorporated that in the chart, that is this horizontally small b by b. So, that means first you have to calculate the small b by capital B ratio, then corresponding to your phi value and the beta value and df by b condition, you determine the factors. Similarly, n gamma q and n c q. And remember that these values are given for only strip footing. Now, if it is for different footing condition, for suppose rectangular footing, but there is no such recommendation is given, but you can use those shape factors and you can multiply with them and you can get the value. So, again as for different cases you can use those factors, those are discussed in the previous classes with this basic equation which is given for the strip footing, and you get the values for different conditions. That means for different footing conditions and other difference factors, because I have now discussed few I mean total 6 factors, but the total 6 you may not be used because your ground factor and base factor, because you have already used the it is on the slope in different way. So, ground factors you no need to apply. So, but other factors you can apply for this one with caution, because it is originally developed for this strip footing and then foundation on the slope. So, this is the values or the chart by which you can determine. So, now I will solve one particular problem. First problem that I will solve is if example problem, that is your foundation base is tilted. The first case I will discuss about the foundation base is tilted one. Okay. So, this is the ground surface, and here the ground surface is again going in the same direction, but now the foundation base is tilted. Okay. And this is your foundation where the tilt angle eta is equal to 10 degree, and obviously beta is equal to the 0 degree in this case. Okay. This is the problem. And a vertical load, vertical to the with respect to the footing, which is acting as the center, that value is equal to 1000 kilonewton. Okay. And on the horizontal load is acting as a 300 kilonewton, and remember that your width of the foundation, this is width of the foundation which is 2 meter. Okay. So, I can write that this is the your foundation with tilted base, this is the B of the foundation width which is 2 meter, and there is a vertical load acting, and remember that vertical load is acting at the center, that means no eccentricity, and this is 1000 kilonewton, and horizontal load which is parallel to this way it is acting, that means it is parallel to B, So, HB is equal to 300 kilonewton. So, that means your V is equal to 1000 kilonewton, HB is equal to 300 kilonewton and HL is equal to 0. So, that means that no horizontal force parallel to length is acting, the horizontal force parallel to B is only acting. So, previous example case I have discussed that horizontal load is acting parallel to L and no horizontal force was acting parallel to B, but it is opposite. That means horizontal force is acting parallel to B, but no horizontal force acting parallel to A. But there is a vertical force acting at the center of the footing, that means no eccentricity. But if there is eccentricity also, then you have to incorporate that effect, as I discussed in my previous lectures. Okay, so now the values, the soil properties are given on thing that your df is a very small value which is 0.3 meter. Okay, and your phi value is given 20 degree, C value say 100 kilonewton meter square, and as I mentioned B is equal to 2 meter and L is equal to 3 meter. Okay. And you consider the general shear failure where A is equal to 2 into 3, that means 6 meters square, and you have to consider the general shear failure because it is a C phi soil, and you consider the general shear failure. But as we do not have that compressibility factor calculation data, so if those data are available, that means the elastic modulus and the mu or the shear modulus and the Poisson ratio mu, then you can calculate the compressibility factors and then check that due to the compressibility of the soil where the any bearing capacity reduction will be there or not. But here those data are not given, and also it is assumed it is a general shear failure. So then we will solve according to that. So this is HL is equal to 0, remember that. So as I discussed in my previous problem, that if HL is not equal to 0, then I have to go for two sets of equation. But here HL is equal to 0, so then I have to go for only one set of equation if I use the Hansen bearing capacity theory. So I will solve this question by using two bearing capacity theories, one is Hansen and one is basic, and then you will find what are the differences between Hansen and the basic, because here as I mentioned in the basic bearing capacity theories, those horizontal either it is parallel to L or parallel to B are already incorporated in the inclination factor determination part, but in the basic it is not incorporated. So that we have to incorporate it by modifying the shape factor, and if it is HL is not equal to 0 by taking two sets of equations, okay, and two sets of factors. But as here HL is equal to 0, then you have to go for one set of factors and the equation. So these things I will discuss, and I will solve this problem in the next class using the same conditions. Okay, same problem we will solve in the next class. Thank you.